First of all, I'd like to thank the Teaching Learning Center of Ramanujan College for giving me an opportunity to talk on optimization problems. This talk consists of two parts. The first part comprises of three existence theorem, which gives sufficient conditions for the existence of a global minimizer, which is followed by an alternative proof of the fundamental theorem of algebra. In the second part, I'll be talking on certain first and second order optimality conditions for the existence of local or global minimizers. Now let us look what we mean by an minimization problem. If I consider a function f defined on a set U in Rn, we can consider a minimization problem of the form minimize fx subject to x belongs to U. There are certain notions like local minimizers, global minimizers associated with this minimization problem. We can say a point x star in U is a local minimizer if the function keeps a minimum value in the neighborhood of x star. That is, there exists a delta greater than 0 such that fx star is less than equal to fx for every x lying in the neighborhood of x star, but for only those points which are coming from U. If this inequality is strict, it is referred to as a strict local minimizer. If this inequality holds for every x in U, we call it as a global minimizer or simply sometimes a minimizer. And if this inequality is strict in the definition of global minimizer, it is called a strict global minimizer. If instead of the minimization problem, if you have a maximization problem, then we can similarly define the notions of local maximizer, strict local maximizer, global maximizer, and strict global maximizers. So let me first illustrate this problem with the help of an example. Let me consider a function f, which is a polynomial of degree 4, and suppose we have to minimize this function on a set U, which is a semi-open interval, which is open at -3 and it is closed at 1. If you plot this graph, it looks something like this. And this graph I have plotted with the help of the site www.geogebra.org. Here we see that the point x equal to -2 is a global minimizer and the value of the function at -2 is -4, and this point is also a local minimizer. Another point which is a local minimizer but not global minimizer is this point, which is half, which is on the right side of 0. You can see there is a dip in the function. Now, instead of a minimization problem, if we consider the maximization problem with the same objective and the same set U, then we can see that there is a peak at x star equal to 0. So 0 is a strict local maximizer. We'll also identify one more maximizer, that is the point 1. The point 1 is a strict local maximizer because we have only to consider the points which are lying in the neighborhood of x star and also lying in the set U. So 1 is also strict local maximizer. Clearly, this function has no global maximizer because the point -3 is not in the set U. The next aim is to find the existence theorem or to prove existence theorem with the help of a concept called minimizing sequence. So let us see what we mean by a minimizing sequence. A sequence has to be taken which is related to the function f. So there is a function f which is defined on Rn. This sequence xn, which is in U, is set to a minimizing sequence if the sequence of images, that is fxn, approaches towards the infimum value of the function f on the set U. So for example, let me consider this graph. This function has a minimum value 0 attained at x is equal to 0. And this sequence clearly is a minimizing sequence because f of 1 by n approaches f0 as n tends to infinity. We can have one more example. Let us look at this example. Minus 1 by n square. This is also a minimizing sequence. If we consider this particular function, we can see that the infimum value of this function is 0, attained at x equal to 0, and the other end of this graph, as x goes to infinity, this function is also asymptotically approaching towards the x-axis. So xn is equal to 1 by n is a minimizing sequence, as well as the sequence xn is equal to n is a minimizing sequence because f of n approaches 0 as n tends to infinity. Now, with the help of this definition of minimizing sequence, we can give the proof of the existence theorem in a very simplified form. Let me just talk about the first existence theorem, which is the famous Weierstrass theorem, which is also called Weierstrass extremum value theorem. This is given by the German mathematician Karl Weierstrass, who is also known for other theorems such as Bolzano-Weierstrass theorem, Weierstrass approximation theorem, Stone-Weierstrass theorem, and so on. So what is the statement of this theorem? It says that every continuous function on a compact set has a global minimizer. And let's give the proof of this theorem, which is very simple. If I take a sequence xn in K, a minimizing sequence, it's easy to see that always a minimizing sequence will be existing. So what is the definition of the minimizing sequence? The sequence fxn will converge to the infimum value. Let me write this value for simplicity. Let us represent it by, say, f star. This f star can even take the value minus infinity. Now, this function is continuous and the set K is compact. So when I look at these points xn, they are in K, and K being compact, we can extract a subsequence which converges. So let me call that subsequence as xnk, and let us say the subsequence converges to x star. Now K being closed, x star is automatically going to be in the set K. Also, f is continuous, x and k goes to x star. So applying the continuity, fx and k goes to fx star. So the sequence itself was going to fx star, whereas the subsequence fx and k is going to fx star. But by the uniqueness of limit, both the values must be same. So we have f star is equal to fx star, but fx star is equal to infimum of fx, x belongs to k. Hence, x star is a global minimizer. So we had given a simple proof of Weierstrass theorem. Now we go ahead and see whether we can give another theorem by relaxing the compactness assumption on K. In fact, we can relax this compactness and have the theorem provided the function has at least one compact sublevel set. So let's see what is a compact, what is a sublevel set. Let f be a function which is defined on D, where D is any arbitrary set in Rn. The sublevel set of f at certain height alpha, which we denote by L alpha f, is defined as the collection of points which comes from D for which the value of the function is always less than or equal to alpha. Let us illustrate this with an example. Let me consider this function which is discontinuous at x equal to 0. Let's look at the graph. It is like this. Now, if I take alpha equal to 2, that means the level is 2. Then what are the points for which fx is less than equal to 2? So the points are between minus root 2 and root 2 except 0, because f of 0 is 3 and 3 is greater than 2. So 0 cannot be in this level set. Similarly, if I take alpha equal to 1, the level set is the closed interval minus 1 to 1 except 0. Also, if we take alpha equal to 0, it is easy to say that the level set is, sublevel set is empty. In fact, for every alpha strictly less than 0, the sublevel set is empty. And for every alpha greater than or equal to 3, the sublevel set is the closed interval minus root alpha to root alpha. Now, with this understanding, we go and prove the next theorem, the next existence theorem. The statement is, if f is a continuous function defined on a set D, and f has a compact sublevel set, then f has a global minimizer on D. Here again, we invoke the concept of minimizing sequence. So we consider a minimizing sequence in D. So by definition, fxn goes to f star. F star is the infimum value of the function on D. Now the statement says there is a compact sublevel set. So let me say this set, that means the level sublevel set with height alpha, is a non-empty compact sublevel set. That means it has at least one member in this set. Now f star is the least value of the function, and this consists of all those points for which fx is less than equal to alpha. So naturally f star will be less than or equal to alpha. Now there are two possibilities. Either our f star will be equal to alpha or f star will be strictly less than alpha. If f star is equal to alpha, then all the points in this set has the value f star. That is, every point in the level sublevel set is a global minimizer. Let us now consider the case when f star is strictly less than alpha. Now fxn is going to f star. So what happens? After a certain stage, fxn's will be all less than equal to alpha for n sufficiently large. That is, there exists a positive integer m such that xn belongs to this sublevel set for all n greater than or equal to m. So these points are all coming in the sublevel set. Now, the rest of the proof is similar to what we have done in the Weierstrass theorem, because this sublevel set is given to be a non-empty compact sublevel set, and also f is continuous. So we have to extract a subsequence of this sequence, and that will be convergent. Because this L alpha f, this sublevel set is closed, x star will be in this, that is x star is in the sublevel set. Again, using the continuity, we have fx and k will converge to fx star. By uniqueness of the limit, we have fx star is equal to f star, which is infimum of fx over d. Hence, x star is a global minimizer. So we have given the proof of two of the existence theorem. Now the third existence theorem is slightly stronger than the second existence theorem, and I would like to give that theorem because with the help of that theorem we can give an alternate proof of fundamental theorem of algebra. The third theorem is actually based on the notion of coercive map. So let's see what is a coercive map or a coercive function. Let me assume f is a function defined on a set D. Then f is said to be coercive if we have this condition. That is, whenever the point x are such that norm of that x goes to plus infinity, then the function fx has to go to infinity. So this somehow captures the minimizers. We are able to capture the minimizer because as we move away from towards infinity, the function is going up. So we are able to capture the minimizers. Of course, the function has to be continuous. We'll see the proof of that. Before that, let's see an example. Let me consider this function f defined on the interval -1 to plus infinity, which is defined like this. Again, this is a discontinuous function and the graph of this function is like this. Is this a coercive function? Let us see. When norm x goes to plus infinity, in the real case, we have two options. Either x can go to plus infinity or x can go to minus infinity. When x is going to plus infinity, we can see f of x is also going to plus infinity. That's so this condition is satisfied. But since the function is bounded on the left side, the function x will never go to minus infinity. So no problem. We don't have to check whether fx goes to plus infinity when x goes to minus infinity. So we can say that this function is cohesive. Now I give an example which is not cohesive. Let's consider the function fx is equal to x cubed. This is the graph of this function. Here what is happening? When x is going to plus infinity, fx is of course going to plus infinity. But the problem is when x is going to minus infinity. X is going to minus infinity. So mod x is of course going to plus infinity. But f of x is not going to plus infinity. It's actually going to minus infinity. So this function is not cohesive. If you have functions like this and it is also continuous, the first example we will be able to capture our minimizer. But if you look at the second function, then you will not be able to capture the minimizer because this is a decreasing function which is going towards minus infinity. So the cohesiveness plays an important role in establishing the existence of a minimizer. So we have this third existence theorem. It states that the function f is continuous. So in all the three theorems, we are assuming f to be continuous. So the relaxation is on the condition of the domain. So we are assuming f to be a continuous function, plus it is a cohesive function. And here I have to also assume that D is a closed set. So there are three conditions: continuity of f, cohesiveness of f, as well as the closeness of the set D. Then f has a global minimizer on D. Now this theorem being stronger than the second theorem, I have only to prove that if for this function, there is a compact sublevel set. Once that is ensured, then by the previous theorem, the existence of global minimizer is guaranteed. So our aim is to show the existence of a compact sublevel set. Let me consider a non-empty sublevel set. It can be any non-empty sublevel set. Let me consider like this. Now, my claim is to prove that this is a compact set. So to prove compactness in finite dimensional case is simply to show the set is both closed and bounded. The first claim is this sublevel set is a closed set. How do you prove a sublevel set is a closed set or any set is a closed set? We have to take a sequence in that set, and if you consider its limit, the limit point should also be in that set. So let me consider a sequence in the sublevel set which converges to X. Now we want to prove this X also belongs to this set L alpha F or this sublevel set. So looking at the fact that D is closed, it is clear that X belongs to D. So the first condition is ensured. X is now in D. Now we have to see whether fx is also less than equal to alpha or not. Xn's are in L alpha F. So we have fxn is less than equal to alpha. F is continuous. So by the continuity, we get fx is also less than equal to alpha. So this point x is also satisfying the second condition in the definition or in the set L alpha F. Hence, x belongs to this set. Thus, the sublevel set is a closed set. Now I need to prove this is also a bounded set. Let us see how we do that. We are going to prove it by contradiction. Let me assume that it is not a bounded set. That means we have a sequence in this sublevel set which satisfy the condition that norm of xn goes to plus infinity as n tends to infinity. Now what do we know about this function f? It is a coercive function. So f of xn will go to plus infinity. Now by the definition, the value of f of xn can be made as big as you want. So if I take alpha to be one of the number, then fxn can be made more than alpha for n sufficiently large. That is, there exists a positive integer m such that fxn exceeds the value alpha for all n greater than equal to m. What does this mean? Xn is not in L alpha f for every n greater than or equal to m. But this is a contradiction because we had taken the sequence xn from L alpha f, this sublevel set, and now I'm saying the tail of that sequence is outside this sublevel set, so which is a contradiction. Hence, we have proved that the sublevel set which we have taken is a compact set, and it being compact, by the previous theorem, there exists a global minimizer. So all these three existence theorem which we have proved in finite dimensional spaces also holds in metric spaces. Hence it holds in the set of real numbers in the space of complex numbers as well. Now we prove the fundamental theorem of algebra using the third existence theorem. What is the statement of this theorem? Every non-constant polynomial of this form where the coefficients are coming from the set of complex numbers has a complex root. This proof is based on this paper, the Fundamental Theorem of Algebra by Tekelson, which is appeared in American Mathematical Monthly in 1976. Let's see the proof. Now let me associate a function f with the help of this p. That is, f is a function from C to R defined as f of z is modulus of pz. Clearly, we can write this modulus like this. That means you divide and multiply by mod z to the power of n and do some adjustment. We can write like this. Now look at the term inside the second modulus. That is in the form of a summation form. Now if I take mod z goes to infinity, the second, third, fourth term in the summation all goes to 0. So what do we have? This modulus term goes to mod of an as mod z goes to plus infinity. Of course, an is non-zero, so modulus of an is strictly greater than 0. So the second term in the modulus goes to a finite number. The first one goes to plus infinity. So modulus of pz goes to plus infinity. That is, fz goes to plus infinity as mod z goes to plus infinity. That is, this function f is a coercive function. So by the third existence theorem, the function f has a minimizer. Let me call z star to be a minimizer of f. Without loss of generality, we can assume z star is 0. If it is not so, we can consider another polynomial of the form 2z, which is equal to p of z plus z star. Then this polynomial q will have 0 as the root. Sorry, as not the root, it has the corresponding function f has a minimizer z star equal to 0. Now z star is a minimizer of f. So what do we have? Modulus of a naught, which is equal to f0. So what is f0? F0 is modulus of p0. P0, when I put all of them 0, it's simply modulus of a0. Modulus of a0 equal to f0 is less than equal to fz for all z belonging to C. Now my claim is this a0 is 0. What is the advantage? If a0 is 0, if I go back, a0 is 0, then you can see that this polynomial will have z equal to 0 as a root. That is our aim. Whatever is the minimizer of this function f, I have to show that is a root of this polynomial. So I have to prove a0 is 0. Suppose on the contrary it is not so. A0 is positive. That means modulus of A0 is positive. And let us write the polynomial in this form, where ak is the first non-zero coefficient after a0 to be non-zero, and q is a polynomial of degree n minus k minus 1. This ak can be even 1. If you have a0 is non-zero, look at a1. If a1 is non-zero, then that k is 1. If a1 does not appear, a1 is 0, then k will be 2 or k will be 3. So you will ultimately be able to find out a k, the first one, which is non-zero, and we can write like this. This polynomial is also a reformulation of the polynomial pz, and so the polynomial qz is of degree n minus k minus 1. Now we have to do some manipulation. So let me say w is a kth root of minus a0 over ak. What does that mean? Wk is minus a0 over ak, or ak wk is minus a0. So this will help me to do the arrive at a contradiction. Now, if I replace z by tw, where t is any real number, later on I'll stick to t being positive. What will we have? ptw is a0 plus ak, tk wk, tk plus 1, wk plus 1, qtb, qtw, that is of this form. And if we rearrange this term, you can write it as 1 minus tk a0. Why? Because ak wk is minus a0. So it is minus a0. So we can take common, a0 common. So it's 1 minus tk. And in the third term, I just keep tk out. And one of the tk I'm keeping inside, twk plus 1 qtw. Now we can see that the term inside this square bracket can be made arbitrarily small by choosing t where sufficiently small, of course positive. That is, if t is between 0 and 1 and it is sufficiently small, then this quantity can be made arbitrarily small. So make it so small that it is less than modulus of a0, which is a positive number. Now, with this choice, what do we have? If I take the modulus of P transpose W, it is strictly less than 1 minus tk A0 plus tk times modulus of A0, which is equal to modulus of A0, and modulus of A0 was f of 0. So what do we have? F of tw is strictly less than f0, where t is a sufficiently small positive quantity. So is this a contradiction? Yes, because we said 0 is a minimizer. Now I'm getting a point tw whose value is strictly less than the minimizer. So we arrive at a contradiction. Hence, our claim a0 is equal to 0 is true, which implies that f of 0 is modulus of p of 0, which is equal to 0. That is, z star is equal to 0 is a root of the polynomial. So we have given a proof of fundamental theorem of algebra, and some of the references which I have used are, this is one of a good book. This is another book which deals with nonlinear programming for a beginner. I have used most of the contents from the third book, which is our course book for Foundations of Optimization by Osman Gullard. This also contains a proof of fundamental theorem of algebra. And this theorem is basically from the paper by Turkelson. With this, I conclude the first part of my lecture. Thank you.